Hello, and welcome to the second part of dimensional analysis. Yesterday, you learned about simpler problems with dimensional analysis, and today we are going to be going over a little bit more complicated versions of dimensional analysis problems. Some things to remember about dimensional analysis is that we use dimensional analysis to convert from one unit to another unit, but it doesn't change the actual value or amount of whatever it is we're talking about. So if we talk about money, for example, if I say that I have $1, that means that I have 100 pennies, but it also means I could have 4 quarters, but it also means that I could have 20 nickels. But the amount or the value of that money is the same. So that's kind of what dimensional analysis does. If we're talking about distance, we can figure out that in 1 mile, for example, there's 5,280 feet. And no matter how you say it or think about it, the length of 1 mile or the distance of 1 mile is the same. So we're going to use some slightly more complicated versions of dimensional analysis. And today we are going to focus a little bit less on the metric part and some more on the standard or imperial measurement system, and sometimes we'll be converting between the two of them. So in the first problem here, we have the question is asking us how many feet are there in 125.6 centimeters. So the very, very first thing that I need to do is I would need to go around and look for or figure out the relationships that I might need. I don't know off the top of my head any direct relationship from feet to centimeters. I'm sure there's one that exists, but I have never learned it, and so I don't know it. But I do know that 1 foot has got 12 inches, and I also am aware that in 1 inch, you could find 2.54 centimeters. So these are the relationships that I found that we're going to use today. So the first relationship that we need to sort of focus on is the fact that 2.54 centimeters equals 1 inch, and that's really pretty important. So just like we started with our problems yesterday, we took our given value, which in this case was 125.6 centimeters. Make sure we put our units in there over 1. And now I'm going to set up a fraction or multiply by another fraction using this relationship or conversion factor. So the way that I want to set my conversion factor up is so that my units of centimeters will cancel out. So I'm going to put centimeters on the bottom. And then because I'm comparing centimeters to inches, I'm going to put inches on the top. So what I'm really doing is setting up a math relationship where I can cancel out my units, which in this case will be centimeters. So I'm now going to fill in my values. So 1 inch is the same or equal to 2.54 centimeters. That's really awful. Sorry about that. Let's see, 2.54 centimeters. Not much better, but still better. Now at this point, if I take this problem and stop, my units for centimeters will cancel out and I'll be left with units of inches. And that's really important. It's a one-step conversion problem, and we did a good job, but we need to go a little bit further because that's not actually solving the problem. So what we're going to do is we are going to go one step further and convert from inches to feet. So in this case, we see that the relationship between inches and feet is that in 1 foot, there are 12 inches. So again, I'm going to set this problem up where I'm going to put inches, or the unit I'm trying to get rid of, which in this case would be inches, on the bottom. And I'm going to put the unit I'm trying to find or get, which is foot or feet, on the top. So I'm going to put my number or my value for feet, which in this case is 1 foot, divided by 12 inches, or is equal to 12 inches rather. And then I'm going to go and check or cancel out my units that I can, which in this case is inches. And so at this point, I can go ahead and calculate out my answer. So I'm going to go and plug this into my phone, or not my phone. That is like the worst thing I could possibly say. I'm going to plug this into my calculator, which is 125.6, and I'm going to divide by 2.54. 25 125.6 divided by 2.54. And then I'm going to divide that again by 12. And I'm going to get a value of, let's see, going to one decimal place, of 4.1 feet. Now, a couple of things I'd like to point out. First of all, you do have to show your work using dimensional analysis steps for problems like this, just like I showed you here. Secondly, we need to see your units all the way through. You can't just put 125.6 times 1 divided by 2.54 times 1 divided by 12 and get 4.1 and then magically write feet. That's not how it works at all. As a matter of fact, that's witchcraft, and none of us understand how that works. So in this case, you have to show that you're canceling out the units. That is really, really, really important. For those of you that are sort of like looking at this number saying, well, how did you get that number? I'd like to take a second to sort of try to explain. So I took, really, because it's a series of fractions, I multiplied by the across the top and then multiplied across the bottom and then divided, which kind of looks like this. If I was going to do it without any units, I would have 125.6 times 1 times 1. And then I would divide it by 2.54 times 12. So I would take one, so that would really give me my 125.6 divided by, and I do not remember off what 2.54 times 12 is off the top of my head. So 2.54 times 12 is roughly 30.48. And so if I take the 125.6 divided by 30.48, I get something like, oh, weird, I get the exact same number, which is 4.1 feet. So that's the math that's really going on here. Sometimes when I put these in my calculator, I'll say in class, like I take 125.6 divided by 2.54 divided by 12. And that's really what I do. But this right here is what's actually kind of happening. So that's the first one. Make sure you can plug that in your calculator and you get the same answer. If you cannot plug that in your calculator and get the same answer as me, please do me a favor and write that down or write a question down. And then next time you see your teacher, myself, Ms. Ham, or Ms. E, we can go through and check and see how you're doing your calculating, because it could be a really simple mistake. That's a really simple fix. All right, so we're going to move on to the next question, which is gallons of gasoline could fit in 3 tons of a 3-ton container. So I went through the trouble of looking up the density of gasoline and how the relationship between pounds and tons, because I'm going to need those things. But before we really get too deep into this, I want to talk about the relationship of density. So what I'm telling you here is that density of gasoline is 5.83 pounds per gallon. So 5.83 pounds per 1 gallon. And so, like, if you mow the lawn for your grandparents or your neighbor or even at your house, you might at one point or another have to walk to the gas station with a little red gas container and go fill it up with gas. If it is a 1 gallon gas container, when you fill it up to the 1 gallon mark, it should weigh 5.83 pounds. So that's what this is telling us, is that the density of gasoline is that for every gallon is roughly 5.83 pounds. But that's really a conversion factor or a relationship that's never going to change. So another way to look at it would be 5.83 pounds equals 1 gallon. Okay, that's another way to look at it. But sometimes we will give you problems and you will be given a density, and that density tells you more information than you think it does. So let's start this problem. So we're going to start with the 3 tons. And I'm going to put it over 1, just like we did in the past. And then I'm going to go from tons to gallons. Well, I don't have any relationship that goes directly from tons to gallons. So what I'm going to do is I'm going to go use the conversion that I found for us before and kind of work our way to gallons. So I found out that 1 ton is equal to 2,000 pounds. So I'm going to set this problem up so that tons are on the bottom and pounds is on the top. And then what I'm going to do is I'm just going to fill in my values. So 2,000 pounds is equal to 1 ton. And if I stop here and cancel out the units I can, I would be left with just pounds. So we know that if we take 3 times 2,000, that should be roughly 6,000 pounds. However, that doesn't actually solve the problem. So now what I'm going to do is I'm going to use my my density of gasoline relationship, which says 1 gallon is equal to 5.83 pounds. And I'm going to flip well, not flip it, but I'm going to set it up so that the pounds cancels out. So I'm going to use the 5.83 pounds, put it on the bottom. Got a little ahead of myself, got really excited. And then I'm going to take the 1 gallon and put it on the top. So in this problem, I'm going to check my units and I'm going to see that pounds cancels out. So tons canceled out, pounds canceled out. So I'm only left with units of gallons, which is good. So I'm going to use that as, that's going to be my unit for my answer. And then I'm going to multiply straight across. So 3 times 2,000, which is 6,000. And I'm going to divide that by 5.83. And I'm going to get a value here of 1,029.15. But because we don't have any decimals in our given, I'm just going to write 1,029 gallons. So in a 3-ton container, you could store 1,029 gallons. And I think that seems reasonable, I suppose. So the trickier part of this one is that if we give you a density, recognizing that a density is actually a relationship or a conversion factor and not just one number. So in this case, the density gave us pounds, the relationship between pounds and gallons of gasoline. In other cases, it might give us the relationship between like grams and cubic centimeters, but it's still a relationship, and that's what's important to remember. Okay, so now we have one more problem that I'd like to go through, and it's a baking problem because in honor of the fact that the Great British Bake Off dropped on Netflix on Friday. So in this case here, we have 6 cups of sugar, and we need to know how many teaspoons are in 6 cups of sugar. And I'm going to be really, really honest. I don't like the empirical measurement system for in the kitchen. I would rather use grams, but we can't change that today. So we need to know the relationship between cups and teaspoons. And to be very honest with you, I have no idea what that is. So what I did is I went and I looked up the relationship between cups and tablespoons. And then I looked up the relationship between tablespoons and teaspoons. So that tells me that I'm going to start with my given, which we've been doing for all these problems, and take 3 cups, or no, I lied, 6 cups. That would have been a disaster if we were making a patisserie. So that would have been 6 cups. And I'll put it over 1. And now I'm going to set my problem up so I can change cups to tablespoons. So I'm going to put the unit of cups on the bottom, and I'm going to put the unit of tablespoons on the top. And I know there's a shortcut, but I'm just going to write it out because I feel like it. So tablespoons. Okay. And now the relationship between tablespoons and cups, we found out here is there's 16 tablespoons. So I'm going to put that right next to tablespoons. Is inside of 1 cup. Okay. And it'd be great if we could stop there, but that's definitely not going to start this problem because that will cancel out cups, but we'll be left with tablespoons, and that's not going to get us the number of teaspoons in 6 cups of sugar. So that means we have to continue on with one further step. So I'm going to start another fraction, and I see that in my relationships up above that I have 1 tablespoon equal to 3 teaspoons. So I'm going to put 1 tablespoon on the bottom. And I'm going to put teaspoons on the top. And so according to the relationship or conversion factor, we see that 3 tablespoons is the same volume as 1 tablespoon. Let me say that again. 3 teaspoons is the same volume as 1 tablespoon. So I think that would be great to know because I can never find any of my measuring spoons in my kitchen, which is why I like to use grams instead. Now, the next thing that we're going to do is we're going to plug this into our calculator. So I'm going to take 6 times 16, and I'm going to take that times 3, and I'm going to get 288 teaspoons in 1 cup. Now, could you imagine if, like on the Great British Bake Off, they were like, well, you have to use all of your measurements in teaspoons? Like, that would be awful, but I feel like it would be really funny. So in this case, this lecture is sort of winding down here. And remember, we're talking about complex dimensional analysis problems, and the things that make these complex are either A, we're going to go from metric to the imperial or standard measurement system, or B, we might throw a number at you like density, and that is a conversion factor or a relationship that you're going to have to be able to decipher, or C, we're going to give you wonky measurements or relationships like teaspoons and tablespoons when we should just be using grams anyway. So if you have any questions while going through this lecture set, jot them down, and then when the next time you see your teacher, be it me, Miss Ham, or Miss E, make sure that you let us know and we can address those questions right away. Otherwise, have a great day.
There are a few more types of complex dimensional analysis problems that we're going to ask you to do. One of these types is rates. So that's where our starting number has both a number on the top of the fraction or conversion factor and a number on the bottom. So for example, in this case, it says Bob is driving 58 miles per hour. So that's my starting point because it's the number in the problem. And really what that means is 58 miles per 1 hour. So because our starting point both has units on top and bottom, it does make this slightly more complex. So we're trying to figure out if Bob is driving 58 miles per hour, how fast is that in kilometers per second? So we have 2 goals here. We need to get miles to kilometers, and then we also need to get hours to seconds. So we're going to start by setting up this problem the same way we've set up our other ones. Just that we're going to have something on both top and bottom. So I've got 58 miles is my starting point on top. And again, we're going to put that over 1 hour. So when you're doing these, it's important to not try to do both halves at the same time. So either start with the top or start with the bottom. It doesn't matter which one you start with as long as you care for both of them by the ends. So I like to start with the top because I don't know, it's just how my brain works. So I'm gonna try to go from miles to kilometers. So if I look over at my factors I gave you, I see there's miles here. And that conversion factor is getting me to meters. Now, based off your lesson yesterday, you should know that we have a relationship between meters and kilometers. So that's going to help us after this. So I'm gonna start by canceling out that miles and getting us to meters because then we can continue to work with that. So again, just like yesterday and the other examples we've done today, we need to keep our units diagonal. So I'm going to put the 1 mile on the bottom. And then I'm going to put the 1,609 meters on the top. So miles cancels, and I'm left with meters. Now that I'm in meters, I can use my kilometers. So take a moment and think about from yesterday, what's the relationship between meters and kilometers? Hopefully you remembered that there are 1,000 meters equal to 1 kilometer. So I can use that next. Again, I need to keep my units diagonal, so I'm going to put my 1,000 meters on the bottom to keep that diagonal. And then I can put my 1 kilometer on the top. So at this point, I'm done with the top. I've gotten miles to kilometers, so that goal is done. My next goal is I need to get hours into seconds. So I have a relationship here that has hours. It tells me 1 hour is equal to 60 minutes. From there, I see that there's 1 minute is equal to 60 seconds. So that should be our route to get us from hours to seconds. Now I didn't space plan very well here, so I'm just gonna kind of whoop, we're gonna pick up down here. So I have hours on the bottom, which means for my next conversion factor, I need hours on the top. So it's 1 hour, because I still need to keep it diagonal. So because it's starting on the bottom, it needs to go on top. 1 hour is equal to 60 minutes. So I'm gonna put that on the bottom. Hours cancels. Now I'm in minutes. To get from minutes to seconds, I look again and I see that in 1 minute, and again I'm going diagonal, so that's on top, is equal to 60 seconds. Minutes cancels, and now I went from hours to seconds, which leaves us in our unit of kilometers on top and seconds on the bottom, so we are good to go. Now I can do my math. So as I do this, remember you're going to multiply anything across the top and divide anything across the bottom. So I'm going to do 58 times 1,609, and then I'm going to hit equals in my calculator. I'm going to divide by 1,000 because it's on the bottom, and I'm going to hit equals in my calculator. Then I'm going to divide by 60 because it's on the bottom, and I'm going to hit equals in my calculator. And then I'm going to divide by 60 again and hit equals in my calculator, and that gets me my final answer. So my final answer, when I do that, I get 0.0259. And because it started out as a compound unit, it's going to end as a compound unit. So this is going to be kilometers per second. Another type of complex problem you're going to have to do is working with square or cubed units. So when we say square, that's my unit squared, just like in math. Or cubic would be unit cubed. This is similar to what you guys did yesterday and today, except we have that added factor. We have to deal with that square or cube. We can't go from a regular unit to a squared unit directly. We have to add in an additional step. So this question is asking how many square meters, so that's what we're trying to find, are in 1.30 square miles. So that's what I'm starting with. The conversion factor I have here is that 1 mile is equal to 1,609 meters, which is the only conversion factor we're going to need. The only problem with it is our units are squared in the problem, but not squared in our conversion factor. So we're going to have to deal with that in a moment. So I'm going to start the same way, 1.30 miles squared. And again, I'm going to throw that over 1. Now I'm going to line up my units just like I normally do. So I'm going to put the 1 mile on the bottom, so that's diagonal. And then I'm going to put the 1,609 meters on the top to keep that. Now the problem is I can't cancel out meters squared with regular meters. So I need to take this whole conversion factor I just put and I need to square that whole factor. So what I like to do is actually separate that out and redo it. So I'm going to put in my calculator 1,609 squared, and when I do that, I get this ridiculous number of 2,588,881, and that's meters squared now, so that's good. And then I can put that over, and 1 squared is just 1 still, so that's going to be 1 mile squared. So now I'm not going to use this for the math. I'm actually going to come this way. And then that'll get us to our answer. So 1.30 times 2,588,881 gets me my final answer of 3,365,545 meters squared. So it's this additional piece of having to square your unit that it is new. Here's another example. How many cubic meters are in 56 cubic centimeters? So what I'd like you to do is pause the video and try this one on your own. When you're ready, you can hit play, and then we'll come back and I'll show you the answer. So go ahead and pause the video. Okay, so looking at this one, our end is cubic meters and our start is cubic centimeters. So thinking back to our metric lesson, I know that 1 meter is equal to 100 centimeters. Again, I'm gonna have to change that to a cubic unit, but that's a good place to start. So I'm gonna start with my 56 cubic centimeters on top over 1. I know that there's 100 centimeters in 1 meter, so I'm gonna put the 100 centimeters on the bottom to keep it diagonal, and then the 1 meter on top to keep it new. I need to cube that whole unit. So again, I did that down below. 1 cubed is still 1, so it's 1 meter cubed. On the bottom, I did 100 cubed, and I got 1 million centimeters cubed. Again, to do the math, I'm going to take 56, my starting number, divided by the 1 million, and then I got 5.6 times 10 to the negative 5th meters cubed, or 0.00056 meters cubed.